We have proved in the previous video that the work done to move a crack tip, or in fact any defect, in a self-similar manner through a distance d zeta is given by d zeta k jk. So in the example that we proved, we moved a crack tip from a point A to point B, and then we showed that the energy change due to this movement of the crack tip, which in this case is the defect, is given by jk d zeta k. Now, the condition here was that the fields, the stress and strain fields due to the crack tip are within this yellow region, and it moves, this region moves in a rigid body manner with the tip of the crack. Wherever the tip of the crack goes, the region of high stress and strain fields at the crack tip moves with it. So this is called self-similar motion of the crack tip, and if this happens, then jk d zeta k gives the change in potential energy of the system. Now we will specialize this to the case of a two-dimensional crack. In order to do that, we have to realize that in the two-dimensional situation, the normal has only two components. So normal has components n1 and n2, and we will use Greek indices to denote them. So Greek indices n beta, where beta goes from 1 to 2 only, will denote the components of the normal. So if you start with the definition of jk, then jk was given, remember, by del v b kj nj ds. We are interested in j1, so we are interested in b1j nj ds. J can take values 1 and 2 only, so we can write this as b1 beta n beta, where beta goes from 1 to 2. Also, b1 beta, if you remember the definition of bkj, bkj was given by w delta jk minus sigma ij u I comma k. So we are doing b1j, so this is j1, this becomes 1. And again, if you think about a plane stress or a plane strain problem, you will recall that in plane stress, sigma 1, sigma 31, 32, 33 are 0, which means that for all cases where I or j are equal to 3, this is 0. In plane strain, sigma 33 is not 0, sigma 31, 32 are still 0, 33 is not 0, but u3 is equal to 0. So u3 comma 1 is also equal to 0, which means that we can write this as sigma alpha beta rather than ij, and this j can be written as beta, and this can be written as alpha. So we have this expression for j1 in case of a plane stress or a plane strain problem. So this j1, now we define a slight variation of j1 as the j integral, which we call j and drop the subscript 1. So this is more or less same as j1, except that it is now evaluated over a special contour which is called gamma. It starts from the lower crack face, goes in an anti-clockwise manner around the crack tip, and ends on the upper crack face. So over this contour, j1 is evaluated, and when that is done, it is called the j integral, denoted by just j. Now consider this. If you take a contour that starts from the lower crack face, goes around, ends at the upper crack face, goes along the crack flanks, then clockwise direction around the crack tip, and then back to the initial point on the lower crack face, then in this blue region you don't have any defects. The crack tip is excluded from this blue region, and therefore J1 when evaluated over this blue region should be equal to 0. It's a defect free region. Further, if you consider the value of J1 on this flank and this flank, you'll see that the normal to this is 0, 1, and the normal to this is 0, minus 1, which means that N2 is the only non-zero component of normal on these two surfaces, gamma plus and gamma minus, and therefore this integrand becomes W delta 1 2 minus sigma alpha 2 U alpha 1. This is what the integrand becomes, plus or minus depending on whether you are on the upper crack face or the lower crack face. Now this is obviously equal to 0, and this sigma alpha 2 is sigma 1 2 or 2 2, both of which are 0 on the upper and lower crack faces. Therefore this term is also 0. So J is identically equal to 0 on this face and this face. Okay, so for a traction free surface, traction free crack surface. So now what about the other faces? So it is non-zero over this contour taken in the anti-clockwise direction, and over this contour taken in the clockwise direction. So if you do that, then over the contour gamma, what you have is J, and over contour gamma 1 what you have is this quantity, and this is taken in the clockwise direction, where this is taken in the anti-clockwise direction. So strictly speaking, I should put a minus here, so that if you take it to the other side, what you have is this integrand evaluated over gamma is equal to that evaluated over gamma 1, where both gamma and gamma 1 are contours that start from the lower crack face, go anti-clockwise around the crack tip, and end up at the upper crack face. So as long as these are contours which start from the lower crack face and end up at the upper crack face in the anti-clockwise direction, these two integrals are equal. But then gamma 1 is an arbitrary contour that I have chosen. So this statement proves that this integrand is independent of the contour you choose to evaluate it. As long as the contour starts from the lower crack face, goes around the crack tip in an anti-clockwise direction, and ends up at the upper crack face, this contour gamma and this contour gamma 1 will give you the same value of the J integral. In other words, the J integral is a contour independent integral. This is an extremely important statement, and let us now use this to solve a small problem. This problem was actually given in a paper by Rice in 1969, where the idea of the J integral was applied to a two-dimensional crack problem for the first time. So this is the problem. This is a thin sheet of material, elastic material to start with a crack. The crack tip is at 0, 0. So this yellow material is sandwiched between two rigid blocks. This one is fixed, this block doesn't move, and this block is being pulled at with a displacement delta naught, fixed. Both these blocks are fixed, so delta naught is constant over this whole region. Now can we evaluate the J integral for this? yes, we can, what we can do is we can now take any contour to evaluate it, as long as the contour starts from the lower crack face, goes around the crack tip and ends up at the upper crack face. So we take this special contour which goes around the crack tip very close to the boundary of the yellow part, so that this is at minus infinity and this end is at plus infinity. The contour does not matter, I can choose any contour I like, so I will choose one which makes it easier for me to evaluate the J integral. So now on this contour, if I look at a point here, this point is almost exactly under uniaxial tension. So epsilon 2 at this point is delta naught, which is the displacement I have given to the upper face, divided by h, which is the thickness of this layer. Why is that so? Because far away from the crack tip at infinity, this point does not know that the crack exists, it's too far away from the crack tip, and therefore this point is it's almost a constant uniaxial tension that you have here, and other strains are 0. Epsilon 1 and epsilon 3 are 0. Epsilon 3 and 1 are 0 because the layer is very large in the one direction as well as in the three direction. So it's a uniaxial state of stress. There is also no reason for shear strains to be present here, because a box, if you draw a box here, it's just going to get elongated. It's not going to change its shape. It's not going to become a rhombus or a quadrilateral. So that's clear from the nature of the deformation. So here on the other hand, at minus infinity, here on the other hand, this is almost like a thin free thin layer, where this at this point, at this location on the crack face, sigma 22 and sigma 12 are 0, and since this thickness is very small, we can assume that sigma 22 and sigma 12 are 0 all through this thickness, similarly all through this thickness. So at minus infinity, x1 equal to minus infinity, sigma 22 is almost equal to 0, whereas at plus infinity, epsilon 22 is delta naught by h, whereas epsilon 1 and 3 are 0 everywhere. So with these assumptions, with these understanding, we can now apply Hooke's law, and it's easy to prove by applying Hooke's law for an isotropic material. For that in this case, sigma 11 and sigma 33 turn out to be nu by 1 minus nu into sigma 22. This is absolutely easy to prove from the fact that epsilon 11 is equal to 0 everywhere. Therefore sigma 11 minus nu times sigma 22 plus sigma 33 is equal to 0, which leads to this equation, and then epsilon 33 is also equal to 0, which will lead to this equation. And solving for sigma 11 and 33 in terms of sigma 22, we easily get this. Now finally use the constitutive equations for epsilon 22. So epsilon 22 is 1 by e sigma 22 minus nu sigma 11 plus sigma 33, but we already have sigma 11 and sigma 33 in terms of sigma 22. So on the right hand side, sigma 22 is the only variable, so we express epsilon 22 completely in terms of sigma 22, and this is what we will get in a situation where epsilon 11 and epsilon 33 are both equal to 0. So under these conditions, this will be the relation between epsilon 22 and sigma 22 from isotropic Hooke's law. Okay, now let us evaluate the J integral over this contour. So now this is your J integral. Gamma is the contour that runs along the edge of this infinite thin strip, and this is how I calculate it. So I start from the left start from the left, go from 0 to minus h by 2 in the x2 direction, minus infinity to plus infinity in the x1 direction, again minus h by 2 to plus h by 2 in the x2 direction, infinity to minus infinity in the x1 direction, and h by 2 to 0 in the x2 direction to end up at the upper crack face, gone in the anti-clockwise direction. Also, here the normal is minus 1 0, here the normal is 1 0, here it is 0 minus 1, and here it is 0 1. So one of the normal components of the normal are 0 always, and we will put that information in. So n beta, when you are going along x2 directions, for example here it is minus 1, here it is n, you are going in the x1 direction, so n2 is minus 1, so beta is equal to 2, so beta is equal to 2 here. Again beta is equal to 1 here, and it's in the plus x1 direction, in the plus plus x1, it's plus 1 in the x1 direction, plus 1 in the x2 direction, beta is equal to 2, and again minus 1 in the x1 direction, and beta is equal to 1. So these are all the terms that will be there in the J integral. And now realize the deformation of this strip. This is a rigid block, so this is just moving as a rigid body by an amount delta naught. So u2 is the only component of displacement. u1 and u3 are 0 anyway, because it's very long in the 3 direction and 1 direction. So derivatives of this with respect to 1 are 0, but derivative of u2 with respect to 1 is also equal to 0, because the displacement u2 does not vary in the 1 direction. It's constant in the 1 direction. And moreover, in this region, x1 less than 0, above the crack, we have assumed that this is thin because sigma 22 is 0 here. We have taken it to be 0 everywhere. So sigma 22 is almost equal to 0 in this region. So with these assumptions that the derivatives of u with respect to 1, u1, u2, u3 with respect to 1 are 0, sigma 22 is 0 in the negative x1 region, we can easily show that out of these integrals, only this term will survive. Only this term will survive. These are 0 anyway. This term will go to 0. This term will go to 0. Only this one will survive. This also will go to 0. So I leave this exercise to you. Please work out why each of these terms will go to 0. Obviously, these go to 0 anyway, because for any value of alpha, u alpha comma 1 is always equal to 0. And just reason out why only this term will survive. So this term is minus h by 2 to h by 2 with w taken at x1 equal to infinity. Remember that this part of the contour is at infinity, and at infinity we have already argued that epsilon 22 is simply equal to delta 0 by h, epsilon 11, epsilon 33 is equal to 0, which means that this is my constitutive equation between epsilon 22 and sigma 22. Now I'll have to calculate w, which is half sigma ij epsilon ij, but I only have to worry about 22, so I'll calculate sigma 22 epsilon 22, and then sigma 22 is given in terms of epsilon 22 by, so this will be half, I replace sigma 22 by epsilon 22, so this is E into 1 minus nu by 1 plus nu 1 minus 2 nu epsilon 22 square. This is what I will get, but epsilon 22 is delta naught by h, so this is delta naught square by h square, and that will be my W evaluated at x1 equal to infinity. So this I have evaluated now, and finally, given that this is my W as x1 tends to infinity, to calculate the J integral from the expression here, I just plug it in. This turns out to be a constant at x1 equal tending to infinity. It doesn't depend on x2. So what I get as J integral is simply this expression. So this is my J integral for this problem. So what does this J mean? Let's turn back to the basic definition. We had proved that it is independent of the contour that we take, as long as we start from the lower crack face, end up at the upper crack face. But in the elastic case, when the material is elastic, we have also proved that if I take the out of plane thickness to be 1, J1 is J1 times d zeta 1 is equal to d pi, and if I take thickness to be 1, this is also the crack area that is generated. So J1 is del pi by del A, which is the same as G. So if you have found the J, which is equal to J1 as we have taken it, the J integral has the same definition as G, provided you have an elastic case. So if you have found the J in the elastic case, you have found the G, and this, for this problem, this is indeed the G as well as the J integral. So that's the significance of it. We have some problems in the problem sheet that I have uploaded, so I suggest that you try them out.